On June 16, 2018, astronomers at observatories around the world received an automated alert. A point of light had appeared in the sky, a point that hadn't existed the night before. Within hours, telescopes across multiple continents swiveled to observe it. What they saw was extraordinary. In just 16 days, this mysterious object became one of the brightest things in that entire region of space. It blazed with an intensity that defied explanation. Scientists scrambled to collect data, to understand what they were witnessing. And then, just as suddenly as it appeared, it faded. Within weeks, it vanished completely, leaving astronomers with more questions than answers. This wasn't a unique event. Every single night, somewhere in the vast darkness of space, cosmic phenomena flash into existence and disappear. Stellar explosions releasing more energy in seconds than our sun will produce in its entire lifetime. Black holes violently devouring stars that wandered too close. Collisions between dead stars that forge the gold and platinum we find on Earth. These are the universe's most violent, most fleeting moments. And they're rewriting everything we thought we knew about the cosmos. Today, we're diving into the cosmic phenomena that appear and disappear, what causes them, how we detect these brief flashes across billions of light years, and what they reveal about the nature of reality itself. Because sometimes, the most important things in the universe are the ones that don't stay. So what exactly are we talking about when we say cosmic phenomena that appear and disappear? In astronomy, we call these transient events. And the name tells you everything you need to know. They're temporary. They're here, and then they're gone. Most objects in space are permanent, or at least appear that way on human timescales. Stars shine steadily for billions of years. Galaxies persist across cosmic ages. When you look at the night sky tonight, it looks essentially the same as it did last night and the night before that. But occasionally, something changes. A new light appears where there was only darkness. An explosion brightens a distant galaxy. A flash of radiation crosses the cosmos. These transient events can last milliseconds, or they can last months. But they all share one thing in common. They're temporary witnesses to some of the most extreme physics in the universe. Think of it this way. Imagine photographing the same landscape every single night for years. Most nights, nothing changes: the same trees, the same hills, the same stars above. But occasionally, lightning strikes. For a brief moment, the entire scene is illuminated in a completely different way, and then it's gone. That's what transient astronomy is. We're watching for the cosmic lightning strikes. But here's the challenge. Space is unimaginably vast, and these events can happen anywhere, at any time. So how do we catch them? This is where modern technology has revolutionized astronomy. We now have robotic telescopes that automatically scan massive portions of the sky every single night. They take thousands of images, and sophisticated computer algorithms compare each new image to previous ones, looking for anything that's changed. When something new appears, a point of light that wasn't there before, the system triggers an automatic alert. Within minutes, astronomers around the world are notified. Telescopes on multiple continents swing into action, racing to observe the event before it fades. Projects like the Zwicky Transient Facility in California, Atlas in Hawaii, and Pan-STARRS are constantly watching, constantly searching. They've discovered thousands of these cosmic vanishing acts. And what they've found is remarkable. Because these brief flashes aren't just pretty lights in the sky. Each one is a cosmic crime scene. Something violent just happened. A star exploded. A black hole fed. Objects collided at relativistic speeds. And we arrive after the fact, piecing together what occurred from the evidence left behind. These transient events are laboratories for extreme physics. They show us matter under pressures we could never recreate on Earth. Temperatures of billions of degrees. Magnetic fields trillions of times stronger than anything in our solar system. Gravity so intense it warps the fabric of space-time itself. Every transient we catch is a unique, unrepeatable moment in cosmic history. And we're learning to read these moments like a language. So what exactly are we seeing when the universe flashes and fades? Let's start with the most famous cosmic vanishing act, Supernovas, the death of stars. A supernova is one of the most violent events in the universe. It's a stellar explosion so powerful that, for a brief time, a single dying star can outshine an entire galaxy of hundreds of billions of stars. To put this in perspective, imagine taking all the energy our sun will produce over its entire 10 billion year lifetime and releasing it in just a few weeks. That's the scale we're talking about. There are two main types of supernovas, and they happen for completely different reasons. The first type, called Type Ia, involves a stellar corpse called a white dwarf. These are the leftover cores of stars like our sun, objects about the size of Earth but containing the mass of a star, so dense that a teaspoon would weigh tons. Sometimes, a white dwarf has a companion star orbiting nearby. The white dwarf's gravity is so strong it can steal material from its companion, slowly accumulating mass over millions of years. But there's a limit. When the white dwarf reaches about 1.4 times the mass of our sun, a threshold called the Chandrasekhar limit, something catastrophic happens. The star can no longer support its own weight. In less than a second, runaway nuclear fusion ignites throughout the entire star simultaneously. The white dwarf doesn't just explode, it completely disintegrates. Nothing remains. The star that existed for billions of years is simply gone. The second type, called core collapse supernovas, happens to massive stars at least 8 times more massive than our sun. These stellar giants burn through their fuel at tremendous rates. When they finally run out of nuclear fuel, there's nothing left to hold them up against their own crushing gravity. The core collapses in on itself in less than a second, and then in one of nature's most violent rebounds, the collapse triggers an explosion that tears the star apart. What's left behind depends on the original star's mass. Sometimes it's a neutron star, an object so dense that a single sugar cube-sized piece would weigh as much as all of humanity. Sometimes the core collapses even further, forming a black hole. But here's what makes supernovas so profoundly important. They're not just spectacular light shows. They're the reason we exist. During a supernova explosion, the intense heat and pressure create nuclear reactions that forge heavy elements: carbon, oxygen, silicon, iron, gold, platinum. Elements that simply cannot be created inside normal stars. When the supernova explodes, it scatters these newly created elements across space. They mix with clouds of gas and dust, which eventually collapse to form new stars and planets. Every atom of carbon in your body, every atom of oxygen you breathe, the calcium in your bones, the iron in your blood, all of it was forged inside stars and scattered across the cosmos in supernova explosions billions of years ago. You are made of stardust. Not poetically, literally, supernovas have also given us something else, a way to measure the universe itself. Type Ia supernovas, because they explode mass, always release roughly the same amount of energy. This makes them incredibly useful as standard candles, cosmic measuring sticks. By comparing how bright they appear versus how bright they actually are, astronomers can calculate precise distances across billions of light years. This technique led to one of the most shocking discoveries in modern science. The universe's expansion is accelerating. This discovery earned the Nobel Prize in Physics in 2011. In 1987, a supernova appeared in the Large Magellanic Cloud, a nearby dwarf galaxy. Supernova 1987A was close enough, only 160,000 light-years away to be visible to the naked eye. For the first time in centuries, people could walk outside and see a star exploding in real time. Astronomers have been studying SN 1987A for over 3 decades now, and we're still learning from it. We detected neutrinos from the collapse. We've watched the expanding debris cloud. We've seen a ring of material light up as the shockwave reached it, years after the initial explosion. But stellar explosions aren't the only cosmic vanishing act. Sometimes, what appears and disappears is even more violent, even more extreme. Imagine a star peacefully orbiting near the center of its galaxy for millions of years, and then, one day, it wanders just a little too close to the supermassive black hole lurking at the galaxy's heart. What happens next is one of the most violent deaths imaginable. We call these events tidal disruption events, or TDEs. And they're exactly what they sound like. A star gets ripped apart by tidal forces. Here's how it works. As the star approaches the black hole, the gravity on the side closest to the black hole becomes much stronger than the gravity on the far side. This difference in gravitational pull, called a tidal force, begins to stretch the star. At first, it's subtle, but as the star gets closer, the stretching intensifies. The star elongates, pulled into a shape like a football, then like a cigar. Scientists have a technical term for this process: spaghettification. The star literally gets stretched into a long strand, like cosmic spaghetti. Eventually, the star can't hold itself together anymore. It tears apart completely. About half of the star's material falls directly into the black hole. The other half gets flung outward into space at tremendous speeds. As the material spirals into the black hole, friction heats it 2 millions of degrees, and it begins to glow brilliantly in X-rays and ultraviolet light. From our perspective, billions of light-years away, we see a sudden flash, a new source of light appearing near the center of a distant galaxy where there was nothing before. The glow can last for months or even years as the material continues falling into the black hole, like water spiraling down a cosmic drain. And then, gradually, it fades as the supply of stellar material runs out. These events are incredibly rare. In any given galaxy, a TDE might happen once every 10,000 to 100,000 years. But because there are so many galaxies in the observable universe, we're now detecting dozens of them. One of the most famous was ASASSN1 for Li, discovered in 2014. Another, a T2019 DSG, made headlines for a completely different reason. It was the first TDE that scientists could directly link to the detection of a high-energy cosmic neutrino. This tiny subatomic particle had traveled across hundreds of millions of light-years, arriving at Earth just as we detected the optical flash. So why do TDEs matter? For one thing, they reveal the presence of supermassive black holes that would otherwise be completely invisible. Most black holes at galaxy centers are dormant, not actively feeding, not producing light, just sitting there in the darkness. But when a TDE happens, it's like someone suddenly turning on a spotlight, revealing what was hidden all along. TDEs also let us study extreme physics in action. Einstein's theory of general relativity predicts exactly how gravity should behave near black holes. And TDEs give us a chance to test those predictions under the most extreme conditions by watching how quickly the star gets shredded and how the material behaves as it falls in. Astronomers can measure the black hole's mass and even estimate how fast it's spinning. Each tidal disruption event is a natural experiment we could never perform in a laboratory. It's the universe showing us what happens when gravity wins. When a star meets its end, not in a glorious explosion, but in a violent, spectacular consumption. But sometimes, cosmic collisions create something even more extraordinary. Now we come to something even rarer, even more spectacular: the collision of two dead stars. These are called kilonovas, and they represent one of the most extreme events the universe can produce. Picture this: two neutron stars, each one a city-sized sphere containing more mass than our sun, locked in a gravitational dance. They've been orbiting each other for millions, perhaps billions of years, gradually spiraling closer as they lose energy through gravitational waves, literally creating ripples in the fabric of space-time itself. Finally, they meet. The collision releases energy equivalent to 1,000 ordinary novas, hence the name kilonova. But it's not just the energy that makes these events remarkable. It's what they create. Think of it as two cosmic nuclear bombs colliding at half the speed of light. The impact is so violent, the conditions so extreme, that something extraordinary happens. Heavy elements are forged: gold, platinum, uranium, elements that can't be created in any other way. For decades, scientists suspected this was how the universe's heavy elements formed, but they couldn't prove it. Until August 17, 2017. On that day, the LIGO and Virgo gravitational wave detectors registered a signal unlike anything they'd seen before. Not the merger of two black holes, which they'd detected previously, but something different: the signature of two neutron stars spiraling together. Within seconds, an alert went out to observatories worldwide. And then, about 2 seconds after the gravitational wave signal, NASA's Fermi satellite detected a burst of gamma rays from the same region of sky. What followed was the most coordinated observation campaign in the history of astronomy. Over 70 telescopes on every continent and in space turned toward a single galaxy called NGC 4993, located about 130 million light-years away in the constellation Hydra. And there it was, a new point of light that hadn't existed before. Astronomers watched in real time as the kilonova evolved. Initially bright in blue and ultraviolet light, it gradually shifted to red and infrared over the following days and weeks. This color change was predicted by theoretical models. It happens because of the radioactive decay of the heavy elements created in the collision. For the first time, we weren't just theorizing about how gold and platinum formed. We were watching it happen. The observations confirmed something profound. Essentially, all the gold on Earth, every gold ring, every gold coin, every flake of gold in your electronics, all of it came from collisions like this one. Neutron stars smashing together billions of years ago, long before our solar system even existed. The same is true for platinum, for rare earth elements used in your smartphone, for the uranium in nuclear reactors. And it confirmed that kilonovas are indeed the source of short gamma-ray bursts, some of the most energetic explosions in the cosmos. This single event, observed in gravitational waves, gamma rays, X-rays, visible light, and radio waves, answered questions that astronomers had been asking for generations. But here's what makes it even more remarkable. Events like this are incredibly rare. In a galaxy the size of the Milky Way, a neutron-star merger might happen once every 100,000 years. We just happened to catch this one, and it changed everything. Yet for all we've learned, the universe still has surprises that leave us completely baffled, which brings us back to where we started. June 16, 2018, the mysterious object that appeared and vanished in just 16 days. Its official designation was at 2018 Cow, but astronomers, with their tendency toward humor, immediately nicknamed it the Cow, and the Cow was unlike anything scientists had ever seen. It was 10 to 100 times brighter than a typical supernova. It appeared incredibly fast, reaching peak brightness in just 2 days, when most supernovas take weeks. And it was extraordinarily hot, with temperatures exceeding 30,000 degrees Celsius. Then, just as quickly as it appeared, it faded. Within 16 days, it had essentially vanished. The Cow didn't fit any known model. It was too bright, too fast, too hot. Astronomers scrambled to observe it with every available instrument: optical telescopes, radio telescopes, X-ray satellites. The data they collected was fascinating and deeply puzzling. So what was it? Several theories emerged. Maybe it was the birth of a black hole or an ultramagnetic neutron star called a magnetar, captured in real time. Maybe it was an unusual type of tidal disruption event. Maybe it was something entirely new. The truth is, we still don't know for certain. What we do know is that the Cow wasn't alone. Since then, astronomers have discovered more events like it, transients with similar characteristics. They've been given equally entertaining names: the koala, the camel, together. They form a new class of cosmic phenomena called fast blue optical transients, or FBOTs. These events are challenging everything we thought we knew about stellar death and cosmic explosions. They're too energetic to be ordinary supernovas, but they don't quite match any other known phenomenon either. And that's what makes transient astronomy so exciting. Sometimes the universe shows us something we've never seen before, something our theories didn't predict, and we have to start from scratch, piecing together the puzzle. The Cow and its cosmic cousins remind us that for all we've learned, the universe still has secrets, still has moments of violence and creation that we're only beginning to understand. But to catch these secrets, we need the right tools. So how exactly do we catch these cosmic vanishing acts? How do we spot a brief flash of light in a universe containing hundreds of billions of galaxies? The answer is a revolution in how we do astronomy. Traditional astronomy was slow and methodical. Astronomers would point a telescope at a specific object, a galaxy, a star, A Nebulians study it in detail. But transient events don't wait for us to be looking. They happen anywhere, anytime, without warning. That's where robotic telescopes changed everything. Facilities like the Zwicky Transient Facility in California scan enormous portions of the sky automatically every single night. ZTF can image the entire northern sky every 2 nights, taking thousands of photographs and comparing each one to previous images. When something changes, when a new point of light appears or an existing one brightens, suddenly sophisticated algorithms flag it immediately. Within minutes, astronomers worldwide receive automated alerts. Achilles, operating from Hawaii, does something similar, constantly watching for objects that could threaten Earth while simultaneously discovering distant cosmic explosions. But here's where it gets really exciting. In late 2025, the Vera Rubin Observatory will begin operations in Chile. This facility will revolutionize transient astronomy. Rubin will image the entire visible sky every few nights with unprecedented depth and detail. Scientists estimate it will discover millions of transient events every single year. Millions. That's more cosmic explosions detected annually than in all of human history combined. The challenge won't be finding transients anymore. It will be processing the sheer volume of data. And that's where artificial intelligence comes in. Machine learning algorithms are now sophisticated enough to analyze images in real time, classify different types of events, and prioritize which ones deserve immediate follow-up observation. The future of transient astronomy is multi-messenger observation. When an event is detected, alerts go out instantaneously. Optical telescopes observe the visible light. Radio telescopes track longer wavelengths. X-ray satellites study the high-energy emission. Gravitational wave detectors listen for ripples in space-time. Neutrino observatories watch for ghost-like particles arriving from the same direction, like GW170817, the neutron-star merger. These coordinated observations give us a complete picture of what's happening, not just a single snapshot, but the full story told in multiple languages of light and gravity. We're entering an era of discovery unlike anything before. Every atom in your body heavier than hydrogen was forged in one of these violent cosmic events. The calcium in your bones came from a supernova. The iron in your blood, created in a stellar explosion. The gold in any jewelry you wear, formed in a neutron star collision billions of years ago. We are not just observers of these cosmic phenomena. We are participants. We are the universe looking back at itself, made of stardust scattered by the very explosions we're now studying. But it's more than just our physical origin. These transient events are laboratories for physics we could never replicate on Earth. Temperatures of billions of degrees. Densities where atomic nuclei are crushed together. Magnetic fields trillions of times stronger than anything in our solar system. Every supernova, every tidal disruption, every kilonova is testing the fundamental laws of physics under the most extreme conditions imaginable. They've also given us tools to measure the universe itself. Supernova observations revealed that the universe's expansion is accelerating, completely rewriting our understanding of cosmic destiny. Kilonova detections provide independent measurements of that expansion, helping resolve one of astronomy's biggest current mysteries. And here's what's truly remarkable. Events that last mere days are studied for decades. A supernova explosion is over in weeks, but astronomers continue observing the expanding debris, the neutron star or black hole left behind, for generations. We're witnessing unique, unrepeatable moments separated by cosmic epochs. Each transient is a singular event in the life of the universe's star's final breath, a black hole's feast, a collision that happens once and never again. The universe is writing its own story in these brief flashes of light, and we're here, finally learning how to read it. Let's think back to where we started. A mysterious flash of light in June 2018. The cow, an event so strange it didn't fit any existing model. We've come a long way in understanding these cosmic vanishing acts. We know that supernovas forged the elements we're made of and helped us discover the universe's accelerating expansion. We know that tidal disruption events reveal invisible black holes lurking at galaxy centers. We know that kilonovas create gold and platinum in collisions so violent violent they shake the fabric of spacetime itself. From rare curiosities to systematic discoveries, transient astronomy has transformed in just a few decades. We've gone from catching a handful of supernovas per year to preparing for millions of transient detections annually. And yet, mysteries remain. The cow and its cosmic cousins still puzzle us. New types of transients keep appearing, challenging our theories, forcing us to expand our understanding. That's the beauty of this field. The universe doesn't wait for our theories to catch up. Right now, at this very moment, somewhere in the vast darkness of space, a star is exploding. A black hole is tearing another star apart. Two neutron stars are spiraling toward their final collision, about to forge elements that will someday become part of planets, maybe even living beings. Most of these events we'll never see. They happen too far away, in parts of the sky we're not watching, at wavelengths we can't detect. But each one we do catch is a window into the universe's most dramatic moments, a chance to witness creation and destruction on scales that humble us. These aren't just abstract cosmic events happening in some distant corner of space. They're intimately connected to our existence. The atoms in your body, the ground beneath your feet, the technology in your hands, all of it created in these fleeting cosmic fires. We are made of stars that exploded billions of years ago. We carry within us the legacy of violence and creation on cosmic scales. And now, we're finally able to watch these moments unfold, to understand them, to piece together the story of how the universe creates, destroys, and recreates itself in an endless cycle. The universe is constantly changing, constantly surprising us. These transient phenomena remind us that nothing in the cosmos is truly permanent. Everything is in flux. Stars are born, they live, and they die in spectacular fashion, seeding space with the raw materials for the next generation. And we're here to witness it. So what fascinates you most about these cosmic vanishing acts? The stellar explosions that created the elements in your body, black holes devouring stars in displays of gravitational violence, the collision that forged every piece of gold on Earth, or the mysteries we still haven't solved, like the cow. Drop your thoughts in the comments below. I genuinely read everyone, and some of the best conversations happen there. If this journey through the universe's most violent moments amazed you, hit that like button. It helps more people discover these cosmic mysteries. Subscribe to the channel and turn on notifications because we're diving deeper into these phenomena. Next time, we're exploring black holes themselves, what happens at the edge of one, what we'd see if we fell in, and the mind-bending physics that governs them. Share this with someone who looks up at the night sky and wonders what's really out there. The universe is constantly writing its story in brief flashes of light across the cosmic dark. And that story, it's stranger, more violent, and more beautiful than we ever imagined. I'll see you in the next mystery. Keep looking up.